Okay, just as a reminder, as you're watching these lectures videos on YouTube, you can increase the quality. If you click on the settings icon on YouTube and go to quality, you can go up to 720p, which will allow you to see the text better. Sometimes by default it's high resolution, sometimes it's not, and that's up to YouTube. I can't control that. So if you're having trouble watching it, just click on that settings and adjust it. Okay, this video is going to be about... Okay, so we're going to talk about recursive functions in this lecture video. Recursive functions are functions that call themselves. Alright, so to start out, we're just going to make a couple of functions that call each other. So we'll make a basic function f of x. That's kind of your standard mathematical function name, f. Alright, and we're going to say f of x returns the value, whatever you pass it, it's going to return x plus 1. Okay, so if I call f of 0 I should get 1. Alright, so I've named this file recursive functions. So this is f of 0. We use node to run it. Okay, f of 0 equals 1. F of 65 equals, should be 66, and then okay, this is about as simple as it gets for a function. Okay, you all should be able to define a function like this. F is just the function name. I could call it anything I want. I could call it foo. It has to start with an alphabetical character. Okay, so f of 777 is 778, right? So it just returns the value of whatever you input and adds 1 to it. Okay, now I can make another function g of some value, let's say y, g of y. That's going to equal, we'll say f of y, return f of y plus 1. Okay, so the f function just adds 1, and so whatever input we give it, which is y, say that's 0, we pass 0 to the f function, and f gets 0 in here, and it says, okay, we're going to return the value 0 plus 1, which is 1. So this whole function becomes the value 1, and then 1 is added to 1. So g of y essentially just adds 2, but the important thing to note is that it calls another function inside of it. It's calling this function. Okay, so let's copy all these console logs, and instead of f, let's call g of those numbers. And they should be 2 more. We'll do it like this. We'll do f of 0 and then g of 0. And we'll do f of 65 and g of 65. There we go. Duplicate that one, make it g. Okay, so basically we're doing f of 0, and g of 0. Now remember, g is calling the function inside of its function body. It's calling the function f of y. Before it can return this value from g, it has to call f of y, and that entire thing has to return a value, and then this JavaScript expression gets evaluated, because this returns one value. A function call is essentially a JavaScript expression, and it has to evaluate fully to one value. Okay? this JavaScript expression consists of a function call, which boils down to a value, and then we add the number 1 to that. Alright? So look, g of 0 basically adds 2 to the number. G of anything. G of n is equal to n plus 2. Okay, so g of 65 is 67. F adds 1, and then g calls f of the number and then adds 1 more. Okay, so we can rename this f, we can rename this add 1 if we wanted, and we can rename g add 2. And so we call add 1 So in Atom, there's a nice feature. If you control F, you can find and replace. I'm going to find the letter G and replace it with add 2, because that's the new name of our function. Click find. I don't want the G in log, but I do want that G. Click replace, replace, find, replace, replace, find, replace, replace. Do the same thing for F. It's one of the nice things about editors, you can find and replace. So F is now called add 1. So we find, replace, 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 replace. Okay. Alright, if you run this, add 1 does exactly what you think it would. You pass it a number, it adds 1 to it. Add 2 does exactly what you think. It calls add 1 and then just adds another 1 to it. Okay, we could also call this add 1 here. We could call add 1 twice, and we get the same value. Okay, so add 2 calls add 1 2 different times. Oops, that's not quite right, because it's going to double it. Okay, because if we do 2 here, we add 1 to 2, that's 3, and then if we add 3 and 3, you're adding more than just the 1. But anyway, the point is, functions can call other functions inside of their code bodies. Okay, the function body here. So essentially in add 2, this section of code here, this function call, gets replaced with all of the code in this function body that has to evaluate. Okay, this is a really simple function, so there's just one line of code. But all this code gets executed and a value gets returned. That all happens here before this entire line can be evaluated. So this function call will evaluate to a value, and then you add 1 to that, and that's the return value. Okay, so that's very basic calling functions within functions. So we can create a recursive function. Call it recurse. And I can say you're going to pass in a number, n, and I'll say if n equals 0, return 0. And otherwise, I'm going to recurse to n minus 1. Okay, so whatever value for n I give it, I'm going to select 1 less than that. I'm subtracting, so if I pass in 10 inside the body of a recurse, n is 10. If n triple equals 0, remember we always use triple equals, if it's 0, then we just return that value 0. I'm going to add a console log in here so we see how many times recurse gets executed. And also value of n. Okay, so let's start simple. I'm going to comment this out for now. We're going to do node recursive functions. I have to call it recurse, and we'll start with 0. Okay. So recurse 0, n is 0. This logs one time. If n equals 0, it returns 0. So that's correct. It's done everything right so far. So let's try recurse 1. Okay, so the first time n equals 1, we log recurse and then the value of n, which is 1. Does 1 equal 0? No, so we skip the if, and then we call the function recurse again. So 1 minus 1 is 0. So here we're calling recurse and passing it the parameter 0, essentially. Then, since we're calling recurse, JavaScript looks up the function recurse. It's right here. We passed in a 0. We're going to log recurse and n. The value of n this time is 0. Does n equal 0? Yes, it does, and we return a value. Okay, so then the value of 0 is returned, and we go back in to our first call of recurse, and this becomes 0. Go ahead and return that value. Okay, let's look at recurse 2. Okay, same thing. N is 2. We log it. Does n equal 0? No. Call recurse again and subtract 1. N equals 1. We log 1. Right, that's here, recurse 1. Does n equal 0? No. Call recurse again. Okay, so we can do this multiple times. There is a limit of how much recursion you can do. There's something called a code stack where all your commands are, all your function calls are kept track of, because we have not finished the original function call. This, when n equals 2, this function is not complete until this other recursive function call completes. So this function is still executing. We just started calling another one before it finished. Okay, so these function calls stack up onto each other, and the program keeps track of which function calls are finished and which ones aren't. It's called the call stack. And there is a limit to how much recursion you can have in most programs. Alright, so recurse 100. There we go. We can see starts at 100 and it just decrements by 1 every time. Okay, so that's very basic recursion. And it's where a function calls itself in its own function definition, or function body rather. Okay. So we'll uncomment these, and we're going to make another. Let's make sure that runs right. Yeah, let's do. There we go. Okay, so some simple output there. So this is really basic recursion. So now let's create a new file. We'll call it Fibonacci.js. Okay, the Fibonacci sequence is a sequence of numbers named after the mathematician Fibonacci. Generally it starts at either 0 or 1, but basically each number, you have to define the first two numbers. So in this sequence, n equals 0, the first Fibonacci number is 1, and n equals 1, which is the second Fibonacci number, is 1. Here you can also start it at 0 or 1, but every number after that is equal to the previous two numbers added together. So the third Fibonacci number is equal to the second Fibonacci number plus the first one. The fourth Fibonacci number is equal to the third plus the second. So 2 plus 1 is 3. This one is the previous two added together, 2 plus 5, or 2 plus 3 is 5. 8 is 3 plus 5. 13 is 5 plus 8, etc. Okay, that's called the Fibonacci number sequence. And we can code this pretty easily with recursion. You find out that it's kind of tricky to code it otherwise. So we start with the number Fibonacci, and we have some value n that we pass into the function. And so we're going to use the one that starts at 0. We're going to use this number sequence. So if n equals 0, we'll say if n is less than or equal to 0, just in case somebody puts in a negative number, then we're going to return the value 0. If n equals 1, we're going to return 1. Okay, so these are the first two cases. They're taken care of. If n equals 0, it's 0. If n equals 1, it's 1. Okay, so let's just console log that. Okay, run the program. Oops, we need to change programs here. Type clear the console, and then node Fibonacci. Okay, so Fibonacci 0 is 0, Fibonacci 1 is 1. Okay, that's good. Now we haven't applied a value for anything else, so JavaScript's going to return undefined because it doesn't know what to do in those cases. For example, Fibonacci 2. Is n less than or equal to 0? No. Is n equal to 1? No. So here, if you leave this blank, that's essentially like saying return undefined. It automatically returns undefined if it gets to that point. Okay, so let's look at Fibonacci 2, since we haven't defined it yet. It's an undefined value. So here's where the recursion comes in. We're going to return Fibonacci, the number we were given, minus 1, so n minus 1, plus Fibonacci n minus 2. Okay, that's what the Fibonacci numbers are. If I have, this is 0, 1, 2, 3, 4. If I have n equals 4, I want to find out Fibonacci n equals 3 and add that to Fibonacci n equals 2. 1 plus 2. So what we're doing is inside of the function body here, we are calling the function itself, but with a different value. So Fibonacci n relies on Fibonacci n minus 1 plus n minus 2. Now this would keep going over and over, except we have these break cases. This is where the recursion stops. These are the exit scenarios. If n is less than or equal to 0, we just return 0. If we didn't have this here, it would just repeatedly call Fibonacci n minus 1 and just keep going and going. But these break cases actually make it return a value, and eventually this gets evaluated to a 0 or a 1, and then this gets evaluated to a 0 or 1. That's added together and returned. Okay, so this is what's called a call stack. You repeatedly call functions within other functions. This first Fibonacci call does not complete until these other two Fibonacci calls complete. These Fibonacci calls do not complete. If they're not one of these two cases, they won't complete until their two Fibonacci calls complete. Okay, so there's a stack of execution that takes place. That's why it's called a call stack. Oops. There we go. Alright, so now this should give us a proper Fibonacci 2 value. It should add 0 and 1 together, which should be 1. We can see, we can do 3. It's going down to 4, 5, 6, 7, 8, 9, 10. Take that and go 11 and 12. Alright, and we'll see what sequence we get here. We run the program. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. And what do we have here? 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. Okay, and it keeps going. So when you think about this, it's very difficult to solve this problem any other way, at least for an indefinite number of n. Okay, so like if I didn't want to use recursion, I could just outline every case, right? I could say if n is less than 0, less than or equal to 0, that's 0. If n equals 1, it's 1. If n equals 2, it's 1. Right? I could just keep doing that, but the problem is I would never have a use case. Whatever number I stopped at in this function, if I went all the way up to 1,000, that's fine. But as soon as I enter in Fibonacci and pass in a number greater than 1,000, I'd get undefined. Recursion allows you to actually solve the problem, and relatively simply, just by code reuse. We're reusing the same function that we defined. So we're calling the function itself within the function body. So we're going to return Fibonacci n minus 1 plus Fibonacci n minus 2. Okay, so that's Fibonacci number sequence. Another good example of recursion is the factorial. You don't have to use recursion for factorials, but you can. It's a good demonstration. So let's do a new file. Call it Factorial. Alright, we have a function and we're going to call it Factorial. And we're going to pass in some number. What is a factorial? Whatever number you pass in is n that number times n minus 1 times n minus 2 times n minus 3 times all the way down until you get down to 1. So it'd be times 3 times 2 times 1 for large cases, right? So this code won't execute. This is just I'm outlining what factorial means. Okay, so in mathematics, 5 factorial, that's the notation in mathematics. This is equal to 5 times 4 times 3 times 2 times 1. Okay, 2 factorial is equal to 2 times 1. 13 factorial is equal to 13 times 12 times 11 dot 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 2 times 1. Okay, so this is difficult because the length of our expression that we're calculating depends on n itself. We're not just adding a number to it, but depending on what number n is, that changes the number of operands. Okay, so we can use recursion here to help us. Let me get this. Do this. I'll put these in the comments so you can see. I'll put this at the top. Okay. So factorial. So the factorial of n is whatever that number is, n times n minus 1 times n minus 2. Well, in this case, take 5 factorial for example. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. But 4 factorial is equal to 4 times 2 times 3 times 2 times 1. Okay, if we add some spacing here, we see that all these terms are the same. Alright, so technically 5 factorial is equal to 5 times 4 factorial. And 4 factorial is equal to 4 times 3 factorial. Right? So this is essentially saying 5 factorial is equal to 5 times 5 minus 1 factorial. So 4 factorial is equal to 4 times 4 minus 1 factorial. See, 4 minus 1 is 3. So 4 times 3 factorial. So what this is saying generically in terms of n, for whatever number n we give it, n factorial is equal to n times n minus 1 factorial. And this is a perfect use case for recursion. Okay, so factorial, whatever number n we provide, is going to equal n times factorial of n minus 1. So dot log. Okay, let's log factorial of now we need our exit case here. Alright, if we don't have an exit case, this will just continually keep recursing until the stack overflows. The call stack can only hold so many function calls. Alright, so we need a breakout case. We know that if n equals 1, 1 factorial is equal to 1, right? Because 2 factorial equals 2 times 1. 1 factorial equals 1. Alright, so that's our breakout case. This will stop the recursion and allow the entire function to resolve. So if n equals 1, so we want to know what 1 factorial is, we're actually going to return a number here and not recurse. So we're going to return 1. So here we'll start out with factorial 1. Clear the console and we'll say node factorial nod. There we go. So 1 factorial is 1. That's correct. 2 factorial should be 2 times 1, which should just be 2. That's correct. Okay, and just to verify, this is 1, this is 2 times 1, this is 3 times 2 times 1, and this is 4 times 3 times 2 times 1. So we're going to log out the values of the actual manual factorial if we write it out, because we know the value of n, so we can write out what that factorial expression is here. So this one is 5 times 4 times 3 times 2 times 1. So if you want, you can add some space here just so they line up and kind of see what terms they have in common. Okay, so we log that. So this first number is the result of calling the factorial function 1, and then we did it manually in the next value. That's that 1. Here, factorial 2, this is the result of calling our factorial function 2. That's 2 times 1, that's 2. This is 3 times 2 times 1, which is 6. And then 4 times 3 times 2 times 1, which is 6 times 4, which is 24. And then 5 times that. 5 times that is 240 divided by 2, which is 120. Okay, so we see that it's working. The nice thing is this is very simple code to do something that's otherwise very complicated to do. In you know, basically 2 lines of code here, I mean 4 lines, whatever. You're doing something incredibly that would otherwise be incredibly complex. And so this is kind of the basis for algorithms. You write an algorithm is basically something you can accomplish by following a series of instructions or steps. So algorithms are very useful because if you can separate a problem into multiple steps, even if you have to redo those steps multiple times, it's very, very easy for computers to do those tasks because of things like recursion and loops. Okay, so you can solve very, very complicated problems that would otherwise be like incredibly difficult for humans to manually do, manually write out the calculations. Computers can do them very, very quickly. Okay. So this is basically it for the introduction to recursion, which again is when you call the function itself inside the function body. So here this is the function factorial. We're calling it with a value of n. Inside the body of this function that's named factorial, we're calling factorial again, but we're calling it with a different value. And this is a simple example because we keep decreasing our value of n. Eventually, if n starts greater than 1, it's eventually going to come down to 1 because we're subtracting 1 each time. So if I had 1,000,000 it would call factorial a million times and subtract 1 each time. Okay, so that's recursion. I will post these in the CS151.00 account under lecture 9. Okay.